And that brings us to the next major tool in our analytical toolbox, total reflection X-ray fluorescence, or TXRF for short. This is our go-to method for surface elemental contamination mapping. So now let's get to that. To appreciate this tool, it helps to quickly understand standard X-ray fluorescence, or XRF. In a typical XRF setup, you shoot an X-ray beam straight down to the sample. That beam penetrates like several micrometers into the bulk material, which is fantastic if you want to analyze, like for example, a solid block of steel. But it is terrible for silicon wafer because the massive signal from the bulk silicon completely drowns out any tiny signal from trace surface impurities. This is where the total reflection in TXRF comes in. So instead of shooting straight down, we utilize grazing angle X-rays, where the primary X-ray strikes a wafer at an extremely low angle so that the beam undergoes total reflection and bounces right off the surface. Because the beam doesn't penetrate deep into the silicon and only the absolute surface atoms are excited, we get more surface sensitive and better detection limit from these measurements. These excited atoms are then emit characteristic fluorescent X-rays, which an energy dispersive detector captures. The result is a direct, highly accurate readout identifying the exact elemental composition of the surface entirely without destroying the wafer. It provides a broad elemental range measuring almost all the elements from sodium through uranium. More importantly, regarding the elements, it offers a distinct non-metal advantage. So you will recall that when we were talking about VPD-ICP-MS, it uses hydrogen fluoride. The chemistry of hydrogen fluoride means that certain volatile and non-metals are lost during the fuming phase. TXRF does not use chemicals, meaning it readily captures critical halogens and non-metals like sulfur, phosphorus, chlorine, and bromine that standard VPD typically misses.